Okay, guys. So yesterday we talked about uh, pair of random variables. Okay, so instead of one random variable, we consider two random variables, and we consider this as a pair. But x and y, these random variables, I mean both of them, they are defined on the same sample space. So yeah, they are defined on the same sample space. So here we had the picture. So this is, let's say, our S, these are sample points. And then this is R, I mean the same R, but let us consider two copies of this. And then this is a way to define this real number. So this is X. And similarly, this is Y. And then we talked about what is called the joint probability distribution function or the joint density function, joint cumulative density function. So basically, we talked about f of xy, or maybe we can say it like this is probability of x equal to x and y is equal to y. So for the case of for the discrete random variable, like when x and y both are discrete random variables, and we also have seen that okay, we can have a table for this. Let's say these are all x here, so these are the corresponding values of x, and these are the corresponding values of y, and then we can have the corresponding points here, x comma y. Okay, so these the parameter here is, let's say, x, small x, and this parameter here is y. Then any point here is like x comma y. And then we said, okay, we can talk about, in fact, this as not just a point, but that is the probability of this. So this is f of x of x. So what is the probability that small x will take this value and y will take this value? So let's say this is x1, y1. So then this will be the probability for x1, y1. So we can have a table format to define the probability mass function or the probability distribution function. And then we also said, okay, we can have, if we have a continuous x and y, the random variables are continuous random variable x and y, then this can be, let's say, some interval, okay, some a to b, and this could be some c to d. Then basically here we have this domain, let's say, um, x, uh, so this is also the area a, you can say, which is defined with set of all xy, okay, such that x is lying from a to b and y is lying from c to d. And then we talked about, okay, let's say we have this z-axis, which is, let's say, kind of a surface, okay. So this is kind of a surface like this, and then we can talked about, let's say, so this is kind of a surface like this, and then we can say, okay, this is the probability surface, or this is f of xy. And then given any, so this is the domain, let's say, or domain can be actually infinite. X can be, let's say, minus infinity to infinity, and y can also be minus infinity to infinity. If it is if it is infinite domain, that can also happen. And then in that case, so this is the entire xy plane, that's the domain, and maybe for different points x comma y, this value could be 0. So the surface is only finite for some particular subdomain, let's say A. And then maybe we are interested to know what is the probability that xy belongs to some A. And then we said, okay, then we can say, okay, this is an integration. If I know xy, the one probability density function, then it is dx dy, which is nothing but the volume under this roof, so that we take a projection and then we get A as this one. So this volume is actually called the probability. This is what we talked about. And then we said, okay, if we have a joint probability density function, okay, similarly, we can define the cumulative probability distribution function. And then we talked about something called the marginal um, marginal random variable or marginal PDF probability density function, which is from the distribution of X and Y, this joint distribution, how to obtain the individual distribution. So that we said what is called the marginal PDF, and then we introduced what is called the conditional PDF, conditional PDF. So then here we said, okay, suppose we're interested about X, but we know that some value of Y had happened. Okay, and then this is a new random variable, it's a conditional, and then what will be the probability of this? So we talked about the PDF of this, and then we said this is a conditional PDF. So this is a conditional PDF, and we denoted it actually f of X given Y. And similar thing we can do like Y, and suppose X has some observed value. So then we talked about, let's say it is G, so Y given X. So this is conditional PDF. Yeah, we talked about that. And so these are basically the new random variables, okay, which are not there in the case of single or univariate case, a single random variable or the univariate case. Since we have a pair of random variables here, then we can of course talk about marginal PDF and the conditional PDF. And then we said, okay, the way we defined different kinds of measure to quantify different properties of a random variable, here also we did the same thing. We introduced the concept of expected value of a joint random variable. Okay, and then we said we denoted it like E of, let's say, XY. And then we talked about something called, this is expectation. Then we talked about moments, and we said moments, and then we said moments are about the mean, moments about the mean. So here the moments was something like this, x to the power r and some y to the power s. And here we said xy product, and here we said, okay, it is expectation of some x minus mu x. So mu x is, let's say, the mean for the marginal distribution of x. And then we talked about, let's say, mu y denotes the mean of the marginal PDF corresponding to y. And then we said, okay, suppose this is to the power r, this is to the power s. So this is the moments are the central moments. So moments about the mean. This is why we defined. And then we said, okay, so for r equal to 1 and s equal to 1, this plays a big role, and we defined this term to be so, which is called the variance, okay, or covariance. So then we talked about what is called the covariance. So covariance is nothing but a value which is E of expected value of x minus mu x times y minus mu y. So when r and s, these are just 1, r value of r is equal to 1 and so s is equal to 1. And then we said that, okay, this will be nothing but expected value of the product of the random variable x and y. So this was a expectation of x times y minus mu x mu y. So this is what we discussed yesterday. Now today we'll talk about some more properties about the conditional mean, conditional variance, and other stuff. And we'll I'll give you an example of a special kind of a distribution of a pair of random variables, which is there in the syllabus. So the fundamental question which we started with is, there's some echo. Let me just check. So there, where this echo is coming from? Okay, I got it. Yeah. So the fundamental problem started with, okay, so suppose we have f of xy, then how this PDF of the joint random variable is related, okay, how it is correlated or related, okay, related with the individual distribution, let's say gx, or the marginal distribution gx, and let's say hy. Okay, and we also talked about when do you say that the pair of random variables x and y are independent, okay? And we also defined that. We said, okay, in that case, there's fxy. If x and y are independent, they are said to be independent. Is independent when the product, I mean, the joint PDF is nothing but the product of the individual PDF or the marginal PDFs. So then there's a pair, this random variable x and y, they're independent, and we have extended this definition also not only for a pair but for any n tuple x1, x2, xn. And we said, okay, if the joint distribution of this x1, x2, let's say xn, suppose we have n random variables, if this can be written as the, let's say the product as a product of the PDF of the individual random variables, then we said, okay, it is independent. And for independent random variable, we also have seen that covariance is 0. So covariance you can, so for independent random variable, we also have seen like sigma, the covariance sigma of xy, this is equal to 0, since E of xy, x times y is nothing but ex times uy, so which is nothing but mu x times mu y. So we have sigma xy equal to 0. So whenever we have independent random variables, then our covariance is 0. But we also had given example. We also had given an example like where covariance is equal to 0, but x and y are not independent. So the converse need not be true. And there is one more parameter which is known as Pearson product moment or product moment correlation coefficient. Correlation coefficient. So we also said it is, or sometimes it is just called correlation coefficient, or some people prefer to call it uh, this Pearson's product moment correlation coefficient. Okay. So yeah. So and this is this number, this measure is denoted by rho, and it is defined as, this is defined as the covariance of xy or sigma xy, whatever you denote, covariance of this by the standard deviation, the product of the standard deviation of marginal random variables or the individual random variables x and y. So then this plays a big role, and if this is the case, then you see we have proved that E of so covariance of xy, right? So covariance of xy was what? So it was mu xy, right? Yeah. Okay, nice work. E of xy minus mu x mu y. This is what we proved yesterday. Yeah. So if that is the case, then using this row, you can just say like, so if you use the definition, so for this will imply E of xy, okay, the product of this random variables, and then its expectation. So this is a new random variable, which is a product of x and y. The sample space is the same, okay? So this, if you treat this as a random variable, it's a z, then z at some omega, okay, is nothing but x omega times y omega. So this is how this random variable is defined. So it's a product of two random variables. And then this then is can be said like this is okay. So if you from here, if you just take mu x in the left hand side, so this plus covariance, and covariance is nothing but rho times sigma x sigma y. So if somehow you know what is this value of this correlation coefficient, so this is actually a measure which will determine how x and y are correlated. Okay, we'll talk about that maybe for a minute. But before that, so if somehow this is known, this correlation coefficient is known, then also you can compute E times of product of this. So this is very useful formula sometimes. Okay, so if you want to know how does it measure? I mean, how x and y are related? How does it give an impression about that? I mean, how does it quantify how x and y are related? So it is nothing. You just use the definition of this. Okay. Then what is that? So if you define the covariance, okay. So then if you just use the formula of covariance, right? So this is covariance of x and y, and this is sigma x sigma y. Of course, sigma and sigma y are positive. And then so you may just forget about this part, and then this is covariance, so it is E of x minus mu x times y minus mu y. Okay, it's just the definition. So this is sigma x and this is sigma y. And if you take the expectation, if you write it down, then what will happen is, okay, this will be double summation and x minus mu x. Okay, x minus mu x, or you can say x minus mu x times y minus mu y. times a for. I'm just using the definition of the expectation. So then you see this guy is a PDF. Okay, the definition of expectation. This is overall x y y. Let's say, and mu y and mu x, they are just a constant. Okay, so x and y are varying only. So this part guy is varying. This guy is varying. This guy is also varying for different x and y. But since this is non-negative, okay, so it doesn't matter. We are looking at the value of rho. So when rho is, let's say, positive, and yeah, when rho is positive or rho is negative. So when this can be positive, so this is a summation. Okay, so this will be positive and only if, let's say, all this term. Okay, if all these terms are positive, then of course this will be positive. And if this is positive, this is negative, or this is negative and this is positive, in that case this will be negative. Okay, so that I mean for all values of xy, if that is the case, so then it is guaranteed that it will be positive or negative. So that means what is happening is x is changing. And so let's say if you have individual, let's say I have something like this is for x. Okay, suppose this is some mu x, so the values of x are here, let's say. Okay, and similarly I can have something here, and let's say this is mu y and these are like y. So what, when it will be positive, say if the value of x minus mu x, when it is increasing, y minus mu y is also increasing. So both are positive. Okay, if that is the case, both are positive. So then that will definitely. So if this gap is increasing, when x is increasing, okay, and then also y is increasing, keeping this value mu x mu y fixed. So then that gives an idea about when it could be positive, when it could be negative. So I'll not go into that because we don't have much time. But this is a clear cut. I mean, this is simple observation which you can prove that rho is lying between -1 to 1. And so when this is positive, some axiom value, we call it positively correlated. Okay, or you can say when it is plus, it is positively correlated, or this is taking the extreme value, it is positively correlated, and it is negative, it is something called negatively correlated. That means when y is increasing, x is decreasing. If that is the thing, what is happening, then we can say they are negatively correlated. Then when one increasing of one value, okay, influencing increasing of the other one, so then that is called positively correlated. So yeah, so this is positive, negatively correlated. So this is one thing, correlation coefficient. We'll use this constant when we'll talk about bivariate normal distribution. But for the time being, we'll just keep it in mind that there is a measure, okay, which measures like how this x and y, this pair of random variables, are correlated, whether they're positively correlated or negatively correlated. Now we'll talk about one important thing. We said, okay, so we have now some idea about, okay, if we have two random variables, we know how to define expectation, we know how to define, let's say, covariance, so we can measure something about this pair. Now, how do you exploit this idea to find out some mean or variance of some other random variables? Okay, that is the question. So here now we'll first talk about the mean and variance, okay, of a random variable, which is a linear combination of other random variables. So this is an important thing, which is like you can always define linear combinations of random variables. So what it means is, let's say you have certain random variables, let's say x1, x2, xn. Okay, then you take a linear combination of that. So then you can define another random variable. So let x1, x2, dot dot dot, like to some xn, let's say. Then there's be random variables. So there could be discrete, there could be continuous, whatever it is. Okay, let's say these are all random variables, and then we can define, yeah, then we can define y, which is so let's say ai xi. Okay, so I equal to, let's say, 1 to n, and ai is some number, ai is some constant. Okay, some real number, let's say. So then this is also a random variable. So as I was telling you one day, that set of all random variables that will also form a vector space. Okay, set of all random variables that will form this will form a vector space, or the field of real numbers. So that's why, I mean, if you take a linear combination of some random variables, so that is always a random variable. Okay, then the question is, what is the expectation of this new random variable? What is the variance of this random variable? Can that be somehow quantified using the variance or the mean or the covariance and mean of some pair of random variables? Okay, so as you know, so without any proof, so we can just say that E of y, so this is the mean of what is the mean of y, because we know that this mean or expectation is a linear function. So definitely this will be sum over ai and e of xi. So we talked about that earlier when we introduced the concept of expectation. Otherwise, what you can do is you just use the definition of mean, and then immediately you'll see that this is what is going to happen. So I equal to 1 to n. Okay, so this is just a formula. Like if I know that means are the expected values of the individual random variable xi, then we can also talk about the mean of the linear combination of those random variables. Okay, this is just a formula, and then and now I'll tell you how to calculate the variance of y and how this covariance will play a role in order to find a formula for the variance. So the definition of variance, if you just recall, it is nothing but some, this is a random variable y, so y minus mu of y, or let's say expectation of y, so this whole square. This is the definition of expectation. So if you just write it down, that what is the y and what is this, so it is y is equal to sum of ai xi, I equal to 1 to n, minus this is anyway sum of ai e of xi, and this is I equal to 1 to n, and then its whole square. Okay, so it is like a minus some b and then its whole square, but this a and b, so there is a summation of other things, right? So the sum, you can take out the sum and you can see what is happening. Okay, you can take the square of it and see. So this is basically expectation of sum over I equal to 1 to n, and then you can say ai, ai also you can take common, so ai xi minus ei, I just write mu I. Okay, mu I, and then its whole square. Okay, so yeah. Where is that? So yeah, so this is what we have. Okay, so this is now suppose we want to find out what is this, because we can use that expectation is a linear function, it will act on this individually. So but so we just have to take, okay, there is one more bracket here, so we just have to consider, okay, I mean, what is the value of this? If we can calculate this, we can do it. So for example, I mean, if you let's just say n equal to 4, then what happen? I mean, if you can take n equal to 2, and then we can see what is happening, n equal to 3, n equal to 4. Okay, then what is happening? It is like, okay, a plus, let's say b plus c plus d, also, or let's say, yeah, the square of this. Okay, so there is, let's say, fourth term. Now, if you do that, what do you get? So it is a square plus b square, and if you just write on the formula, a square plus c square plus d. So if you just expand it, okay, you'll see that it is 2ab plus 2ac and so on. Okay, plus 2cd, let's say. So basically, and then this expectation will act on this individual terms. Okay, so basically, this term will be equal to sum over all these individuals square, and then there will be a common 2, and then there will all the product terms. So each term like a, b, c, d here is like ai xi minus mu I. Okay, so if we just take first the individual terms, if you just take the individual terms first and then the product terms, then it will be nothing but ai square. It will be just ai square, and then xi minus mu I whole square. Okay, so and then you are taking the expectation, so it will be just expectation of this, and then plus there will be a term 2, and then there will be sum of this. Okay, and then there will be ai aj, and you'll see that this I and j, you can just write I less than j, otherwise it will repeat. So that's why this 2 term is coming. Okay, and I equal to j is already being considered here, so it is I equal to 1 to n, and then this will be a of, okay, a of x minus mu I times y minus mu j. So this is what is going to happen. So then we can write this as sum over I equal to 1 to n ai square, and then it will be just the variance of xi plus as 2 times sum over I less than j. Okay, ai, this is double sum, ai aj times covariance of xi xj. So this is a formula for calculating the variance of a random variable, which is a linear combination of this. And here also you can check that we have used a fact, which is covariance of xi xj is exactly equal to covariance of xj xi. You can just check that this is the case. Okay, it doesn't matter. Yeah, so so this is a nice formula. Okay, although a little complicated, but you can just remember this. Okay, that this is individual term. Now if let's say when these values are zero, when this can be zero, for example, let's say if x1, x2, xn, if these random variables, if they are independent, okay, then obviously covariance is zero. Okay, so like you consider a basis of the random variable or maybe linearly independent random variables. Okay, x1, x2, xn, they are linearly or they are independent random variable kind of a thing. Linear or just independent random variable, and then what will happen? And suppose we have this xi or ai xi linear combination of this, and then what will be the variance? The mean is, of course, the formula is the sum of the linear combination of the means of each individual random variable xi. Then you just replace this covariance to be equal to 0 because they are independence. If I just replace this to be equal to 0, this value will be 0. So then we just have sum over all ai square, sum sum over all ai square, okay, variance of xi. So I over I equal to 1 to n. So this is the formula when xi is linearly independent. Okay, so for example, let us solve a problem. Suppose it is given that suppose we have three random variables x, y, and z, and suppose mu x is equal to some 2, mu y is equal to some -3, and mu z equal to, let's say, 4, and let's say sigma x square, I mean the variance of x is equal to 1 something like this square equal, let's say, 5, and sigma g square is equal to 2. And also, let's say it is known somehow that covariance of xy equal to, let's say, -2, and covariance of, let's say, xc is equal to, let's say, -1, and let's say covariance of yz equal to 1. Then suppose the question is find, okay, the mean and variance, okay, of let's say a new random variable, which is a linear sum of these random variables, which is, let's say, w, which is, let's say, 3x minus y plus 2z. Then you can use the formula which you discuss. Okay, you can use the formula and you can, of course, find the mean and variance of this random variable. So this is a typical example of this kind of thing. Now there is one more thing. Suppose there is a more general one more generalization of this is that suppose we have x1, x2, xn. These are the random variables, and let's say y1 is a new random variable which is of, let's say, ai xi, I equal to, let's say, 1 to some n1 or let's say n, and let's say y2, which is, let's say, sum over all ai or let's say bi xi, I equal to 1 to n, let's say, and where ai bi are all, let's say, constants. Then suppose the question is, what is the covariance? Okay, what is the covariance of y1, y2? So this kind of problems practically occur in data analysis. So you have to find the covariance of two random variables, who are each of this random variable, okay, it depends on some other random variables, which is linearly, okay, like the linear combination. So I'm just giving you the ready-made formula, but the formula can be approved. Okay, it can be proved using the same technique which we discussed before. So then this can be written as I equal to 1 to n ai bi variance of xi plus sum over I less than j. So ai bj plus aj bi times covariance of xi xj. Now here you see this formula. What is the difference between this formula and this formula? Here, okay, this formula. See here it is x square ai square, okay, and the latter case which we just discussed, this is ai times bi. Here it is ai times bj, and there is 2 here, but here now it is ai bj plus bj ai. So this is only the change. That means what is happening here? That's what is happening here. Basically, variance is variance of some random variable y. Let's say it's nothing but covariance of y and y. So because if we just replace this this y2 as y1, if we replace the y2 as y1, then this formula reduces to the variance of y1. So covariance of y comma y, okay, is nothing but the variance of y. So this is an important thing, just an observation. Okay, so this is just how these two things are linked. And anyway, so this will vanish again. This guy will be 0 when xi and y xj, they are linear. So x1, x2, xn, let's say they are all linearly independent. And then of course this guy will vanish, and you have a simple formula like this. Only this part, let's say, as the formula for the covariance of y1 and y2. Okay, now we'll talk about conditional mean and conditional variable, because we talked about, okay, suppose we have a pair of random variables x and y, and then we introduce a new random variable which is called the conditional random variable. Okay, so conditional random variable, which was like, okay, given x, given y, some relation of y, how x is distributed. Okay, so this is my new random variable, let's say. Okay, is defined as this way. So when y is observed, y is taking some value, then how x is distributed. So this is the notation. Let's say this is so yeah. So this is my random variable. Let's say this is the notation, and we already have talked about what is called the density function. Okay, x given y. Okay, the density PDF. Okay, or this of this random variable. Okay, we already know this. Now the question is, so since this is a new random variable, okay, if you just remember the picture from yesterday, okay, let's say this is x, this is y, and then this will take some realizations here, y1, y2, dot dot dot. This is all x1, x. For the case of discrete random variable x1, then we said, okay, this is nothing but this is, let's say, small y, or let's say this is small y. Okay, and so then we want to find out, like, under this particular condition. So we are not interested about all other values of y, but when y is equal to this, then how x is distributed. So then what are the values around this point? So this is what we want to find out. What are the heights? Height means this is the probability, let's say, f of xy. What is happening? I think I need to start a new page for this. Yeah, so this is what is the conditional one, right? Okay, so now we'll define what is the mean and variance of this random variable. So we'll now introduce the concept of what is called conditional expectation. Okay, so let us first introduce this for a discrete random variable. So let x be a discrete random variable, and let's say f x given y, okay, is the conditional PDF or probability distribution of x given y is equal to y. Okay, then we define the conditional mean or conditional expectation, okay, of a function of u or function of x given y. So this is important, given y equal to y. So this is conditional. Okay, if u is equal to the identity function like ux equal to x, then of course it is the conditional mean. But here we are defining in a general sense. So it is, we are trying to define what is expectation of ux. Okay, when y is known. So this is what we are trying to define. So this is the same way, same definition. So it is like ux, the values of x, and then times instead this probability, right? So here the probability is x given y. That's it. And this is the definition of conditional expectation. And if x is continuous, this summation will be replaced by integration. If x is continuous, I mean, this is just a standard definition, but since the random variable has changed, everywhere will replace x given y. Everywhere, so this is ux, but since it is for given y, so we everywhere will replace as this one. So then if it is continuous, okay, then if we have some function and given then y, okay, then this can be defined as minus infinity to infinity ux f of x given y dx. So I am just including this x given y, only the change, that is only the change, everything is same. So now, so if ux equal to x, so this is what our interest is. If ux equal to x, let's say, I mean, it need not be x, but it could be x square. Suppose you want to find out the conditional mean of x square given y equal to 1, or some x to the power r given y equal to y. So you can talk about the moments about the mean, everything you are now you can consider for this conditional random variable. Okay, so if u is equal to x, so this is called the conditional mean, and this is denoted at mu x given y. So this is nothing but expectation of x given y. Okay, similarly, conditional variance, same definition, variance, only the change is there will be a given y. Conditional variance, this is sigma square x given y. So this is expectation of the same definition, x minus mu of x given y whole square given y. So and this you can again prove that using the same way, the way we proved it earlier things. That okay, so the similar trick which you used earlier, you can just show that this will be nothing but e of x square given y minus mu of x given y square. Okay, so for the case of without condition, if we recall that we had this one, x square minus e of x whole square, right? So the same thing is here, only thing is that there is given y. Okay, so let us consider an example. So let's say, suppose, okay, we have this joint PDF xy is equal to, let's say, 2 by 3 x plus 2y. I think example earlier, less than 1, 0 less than 1, 1, and let's say 0 otherwise. So let us see an example. An example is, let's say, suppose this joint PDF is given to us, which is 2 by 3 x plus 2y, and when 0 less than x less than 1, 0 less than y less than 1, and 0 otherwise. And suppose you want to find, okay, find the mean and the variance of x given some relation of y, let's say y equal to half. So what you have to first, you have to first find out f of xy. So this first we have to find out, and we found it out for this particular. So we are considering the same example. We can just go back and see this was 2x plus 4y by 1 plus 4y. You just use the formula. Okay, that's it. 0 less than x less than 1 and 0 otherwise. So if that is the case, then we know that then f of x given y is equal to half. So this was, I think this was also calculated yesterday. So this is 2 by 3x plus 1 when 0 less than x less than 1 and 0 otherwise. And then we want to calculate this mu of, okay, mu of x given half. Okay, so this is nothing but expectation of x given half. Okay, so this will be then just use the formula 0 to 1 fx dx. Okay, x fx dx. So 2 3 this x x plus 1. So x fx dx, and you can see that this is 5 by 9. And now you want to calculate the variance. So then you have to find out the expectation of square of it. So x square given half, which is 0 to 1, x square. So 2 by 3 is constant, x square, x plus 1 dx, which will be equal to 7 by 18. And then, of course, we can calculate the variance now. So then variance of x given half will be nothing but 7 by 18 minus 5 by 9 square of it. So this will give you some value. That's the answer. So if you want to find out the conditional mean and conditional variance, everything is same. All the formulas are same, except the fact that you have a conditional term. That's it. Now, okay, so we have built up all the concepts. Now we'll talk about some spatial distribution, distribution PDF. Okay. So in fact, there is, okay, so now go back to our original question. We had xy, we had f of xy, and there was the conditional x, gx, and hy. Okay, these are the marginal, and this is the joint. Okay, this is joint, and these are the marginals. Now the question is, what kind of function? Suppose I would say a pair will have some kind of a distribution. Let's say when you call a pair of random numbers will have, let's say, normal distribution or geometric or uniform. Okay, all this distribution you can think about, but it is, I mean, you can look at the literature and then you'll find is what you can find is that when you are taking a pair of random variables, most of these distributions will not appear in a standard sense. Like, so we cannot say like X will follow Poisson distribution. So that kind of situation will not have. So we have only one special example of a pair of a distribution of a special, special distribution of a pair of random variables, which is known as normal. Okay, so when do you say this density function is following a normal distribution? Okay, so this is the concept which is called bivariate normal distribution. And this is very important because it has some special property. So property means, okay, I will come to that. But so let us first define what kind of PDF this is. Okay, so let's say a pair. So now recall the definition of normal distribution for a single variate case or univariate case. So that PDF, okay, was defined in terms of some mean and variance. So used to denote it as n mu sigma square, right? So there are two parameters, mu and sigma square. Here also the same thing happens. Okay, so okay, let me just write. Suppose, or let's say a pair of random variables, okay, x and y, okay, said to have, said to have a bivariate normal distribution, okay, distribution if the joint PDF, okay, is of this particular form, is given by f of xy. This is also defined in terms of parameters, and actually there are 4 parameters. So this is like this. Is 2 pi sigma 1 sigma 2 square root of 1 minus rho square. Okay, and here it is e to the power. This is e to the power minus 1 by 2 1 minus rho square, and then x minus mu 1 by sigma 1 whole square minus 2 rho x minus mu 1 by sigma 1 times x minus mu 2 by sigma 2 plus y minus mu 2 by sigma 2 and then whole square. So, and then there is a bracket. So this is, so there are basically 4 parameters, but there is one more parameter here. Okay, here x is from -∞ to infinity, y is also from -∞ to infinity, and there's one more parameter, this rho. Okay, and actually you can show that rho is nothing but that correlation coefficient I talked about. Okay, so this is a constant, the correlation between that x and y, where x and y are nothing but the marginal distributions of this pair of distribution of PD, joint PDF. Okay. So in fact, so why this is important, this normal distribution. So if you want to see the picture of this, okay, so -∞ to infinity, let's say x and y, okay, they both are directed. So it is -∞ to infinity. So it is, let's say, x-axis, and this is, let's say, y-axis, and then you have this, okay, and this is, let's say, f of xy. So like you have something like this kind of, how do I draw it? So yeah, so this kind of this kind of a distribution, I mean this kind of a umbrella like under like surface here. Okay, and so what will happen is, this also talked about when you talked about math one, if this kind of a thing we have, and if we, let's say, talked about marginal distribution, okay, and then that will also be a normal distribution. So this is important because for a joint PDF, for bivariate normal distribution, the PDF is bivariate normal, then its marginals are also normal. So this is what is the most important thing. And when they are saying, we are calling it a normal, then question will be, what are the parameters? So here the parameters will be mu1 sigma 1 for the first, let's say x marginal, and for the y it will be mu2 and sigma 2. Okay, so those will be the parameters. So we can calculate this. I think time will permit us for 2-3 minutes, or maybe I will exit for 5 more minutes today. I mean, we have to go very, we have to do this because we have exam on 6th of April, and this is in the syllabus, in fact. And we have only one more day left because next Tuesday only left because Monday is a holiday. Okay, so now if you want to find out the marginal, okay, let's say cross the marginal distribution of x, okay, marginal distribution of x, then what we'll do? So let's say this is gx. So how can this can be found out? So this is thus you have to take the integration over all y. That's it. So instead of some, because this is a continuous case, we have to take the integration. So we just take out, we have to take the integration over all y. So let's say -∞ to infinity and something in terms of y, and then dy will be here. So whatever possible from this fxy, I'll take out all the terms which involves only x. So I'll take out that outside the interval, okay, outside the integration. So then you can see this gx will be nothing but -1/2, 1 minus rho whole square. This is just manipulation, 1 minus rho square. What did I write? Oh, not the whole square actually. So this is 1 minus rho square. Was it 1 minus rho square? No, I think it was whole square. So sometimes it's very confusing. Yeah, whole square, I think. Yeah, that was, but here it will be, I think, 1 minus rho square when you compute that. And then x minus mu1 by sigma 1 whole square, and then this is 2 pi sigma 1 sigma 2 square root of 1 minus rho square, and then here you'll have all the terms involving y. So here we have 2 times 1 minus rho square, and then you have all the terms y minus mu2 wholes by sigma 2, I think, yeah, whole square, and minus 2 times rho times sum x minus mu1 by sigma 1 times y minus mu2 by sigma 2. Okay, and then it is dy. So what you do is how to solve this problem. So the general trick when you use the for the case of single random variable, we wanted to show those parameters mu and sigma square, they are actually the mean and variance. The trick we used, okay, is nothing but, okay, this making the perfect square. Okay, same thing we'll do it here also. Okay, if you recall. So here, let's say we introduce two variables. Let's say u and b. U is equal to x minus, let's say mu1 by sigma 1, and let's say v is equal to y minus, let's say mu2 by sigma 2. Then what happens is gx. Then gx will be nothing but e to the power minus 1 by 2, 1 minus rho square u square, then 2 pi sigma 1 square root of 1 minus rho square, then minus infinity to infinity e to the power minus 1 by 2, 1 minus rho square, v square minus 2 rho uv, and then you will have dv. And then you try to again make this perfect square, so this term. So then what will happen is v square minus 2 rho uv. This is nothing but, if you want to make it a square, this will be v minus rho times u square minus rho square u square. So now you plug into this here again, and then what you see is that gx is e to the power minus half u square, then sigma 1 square root of 2 pi, and then here you'll get 1 by square root of 2 pi, 1 minus rho square minus infinity to infinity, e to the power minus half, and I think then just a v term will remain v minus rho u by square root of 1 minus rho square, and then its whole square, and then dv. And here you can see that this the term inside this, let's say the bracket, okay, so this is just a normal density. This is just again a normal distribution. So then this value will be nothing but 1. And then ultimately we have gx equal to e to the power minus half u square, and then sigma 1 square root of 2 pi, which is nothing but 1 by sigma 1 square root of 2 pi e to the power minus half x minus mu1 by sigma 1 whole square. So this is the marginal distribution. Marginal distribution also. So now you can say like the PDF is nothing but normal mu1 sigma 1. Okay, so this is actually the again normal. So what is happening here when you have a bivariate normal distribution, okay, which is this is the PDF, joint PDF. Then you can calculate that. So there are 4 parameters, mu1 sigma 1, mu2 sigma 2, and there is another for the rho. This is the correlation coefficient, okay, between the x and y, the marginal distribution, okay, the marginal random variables x and y. And that can be proved. You can prove that, okay. And so here among these other four parameters, mu1 sigma 1, mu2 sigma 2, one can show that if you find out the marginal distribution of x from this PDF and the marginal distribution of y, then they'll also follow normal, and the mean and variance of those marginal distributions are nothing but mu1 sigma square for x and mu2 sigma 2 square for y. Okay, so now I'll just give you 2 formula. So this is an interesting thing. So okay, now I'll give a very ready-made formula. Suppose, so this is an observation. You can prove it, but let us, I mean, just using the standard definition, you can prove it. Suppose x and y, they are both, I mean, x and y, they are continuous random variable, and they have bivariate normal distribution. So they are distributed according to bivariate normal distribution. And then what we have seen that the marginals are also normal. But what about conditional density function, or density, yeah, conditional density of let's say y, or let's say x. Okay, so then we say the conditional, this is the formula I'm giving, but it can be proved. The conditional, okay, density or conditional mean, okay, and variance for x, okay, when y is known, okay, are given by this. This is standard formula, which is mu, so x given y. Okay, so then this is mu1 plus rho sigma 1 sigma 2 y minus mu2, and the variance sigma square x given y is sigma 1 square 1 minus rho square. So this is when x given y. Similarly, we can say the conditional mean and variance for the PDF, let's say y given x. Okay, these are the following. So mu y given x is mu2 plus rho sigma 2 by sigma 1 x minus mu1. And then, I mean, whatever the value of x is, the same value will be put here. Okay, similarly here, whatever the value of y is, same value of y will be here. Okay, and sigma square y given x is sigma 2 square 1 minus rho square. This is a formula. Now, interestingly, here you see this rho is playing a very big role. Rho. So rho you can think of like influencing all the formulas. This row, what is that? This row here, this row here. So this correlation coefficient is very important. Okay, here is an example where you see that correlation coefficient that will measure how two different random variables are correlated. Okay, this is very important when it comes to a formula of conditional mean and conditional variance. Okay, and in fact, you can also prove the following: like if this is actually if and not if. So let's say if two random variables, okay, have bivariate normal distribution, then distribution, okay, then they are independent, okay, if and only if rho is equal to 0. So when you talk about bivariate normal, okay, so this is an if and only if condition that if you have a bivariate normal distribution, then you know the marginals are also normal and you know the parameters also. Now the thing is, okay, what kind of questions may come is like, suppose you are given supplied with a kind of a function which is a very peculiar form, but you can make it in this particular form to observe that this is bivariate normal. From there you can find out mu1 sigma 1 mu2 sigma 2, and then probably you'll be asked to calculate something. So for the case of bivariate normal, you know that the marginals are normal also, and there is also a coefficient this rho. Okay, and you can just put this value of rho to be equal to 0, and then you will see that x and y are independent, and then so this can be written as a product of this function can be written as a product of PDF of two normal distribution. One is corresponding to the parameters mu1 sigma square, another one is corresponding to the parameter sigma 2 mu 2 sigma 2 square. So rho is actually binding everything together. This marginal distribution is binding together, and this is producing the joint normal distribution or the bivariate normal distribution. So this correlation coefficient, this plays a big role in order to understand how two different random variables are interacting with each other. And so it's mu1 mu2, like for if you just draw the normal bivariate normal, you will see that I said, okay, so there will be something like this. Okay, there will be something like this, and let's say, yeah, so let's say there is something like this. Okay, something like this, okay, then the maximum value, okay, this maximum value here will be at the point mu1 mu2. So when you are starting this surface, okay, this maximum value will be at mu1 comma mu2. So this is the mean of the pair of means of the individual marginal distribution. Okay, I think we have to stop here. Next day we'll have 1 more hour. Tuesday we'll talk about function of random variables. I'll talk about a particular technique, and that will be the end of the probability theory part, and then we'll be talking about sampling and statistics and probably CLT, the central limit theorem. Okay, so if you have any question, you can ask me, but anyway, guys, I have to I have to be a little fast because